Dear students, this is the first session of Nuclear Magnetic Resonance Spectroscopy of 6th semester Chemistry DSC 2B. Contents of this session are Introduction to NMR Spectroscopy, Theory of NMR Spectroscopy, Equivalent and Non-Equivalent Protons. Introduction to NMR Spectroscopy. Nuclear magnetic resonance spectroscopy involves absorption of electromagnetic radiation in the radio frequency region. Absorption of radio waves in the presence of magnetic field is accompanied by a special type of nuclear transition, and for this reason it is called nuclear magnetic resonance spectroscopy. The source of energy in NMR is radio waves, which have long wavelengths and thus low energy and frequency. When low-energy radio waves interact with the molecule, they can change the nuclear spins of some elements, including proton and carbon-13. Advantages of NMR spectroscopy. Nuclear magnetic resonance spectroscopy is a powerful analytical technique used to characterize organic molecules by identifying carbon-hydrogen frameworks within the molecules. Two common types of NMR spectroscopy are used to characterize organic structure. Proton NMR is used to determine the type and the number of hydrogen atoms in the molecule. Carbon-13 NMR is used to determine the type of carbon atoms in the molecule. Together, NMR and MRI revolutionized the practice of chemistry and medicine by providing fast, non-destructive, and non-invasive means for the observation of matter from the atomic to the macroscopic scale. MRI is an application of NMR, an analytical tool of chemists found in laboratories worldwide. MRI has become a staple of medical diagnostics. Millions of Americans have had an MRI. It is a useful, non-invasive, and non-destructive diagnostic tool for imaging soft tissues such as the brain, heart, and muscles, and for discovering tumors in many organs. NMR is used in the search of biomarkers of infectious diseases like tuberculosis, malaria, pneumonia, neurological disorders, Parkinson's disease, cardiovascular diseases, and risk stratification. Some of the isotopes of elements have the nuclei that behave as though they are spinning about their axis. Such spinning nuclei behave as tiny bar magnets. The angular momentum of these nuclei depend upon the spin quantum number I. This is the theory of NMR spectroscopy. Spin quantum number I assumes values ranging from 0, half, 1, 3 by 2, etc. The relationship between I, the mass, and the atomic numbers are given below. If the mass number is odd, atomic number is odd or even, the spin quantum number will have these values, and these are the examples. If the mass number is even, atomic number is even, spin quantum number will be 0. These are the examples. If the mass number is even, atomic number is odd, spin quantum number will have these values, and these are the examples. Many nuclei do not have spin. They have spin quantum number 0. Hence, they are non-magnetic. When a spinning nucleus is placed in an external magnetic field, the nucleus can take up two I+1 orientations with respect to the field. So the nuclei with I is equal to half can have two orientations, one parallel and another antiparallel to the applied field. A proton placed in an uniform magnetic field H0 may assume two orientations, one of lower energy parallel to the applied field and the other of higher energy antiparallel to the applied field. When the compound is placed in a uniform magnetic field, is irradiated with electromagnetic radiation of proper frequency, the nucleus in the low energy spin state absorbs energy and gets converted to high energy spin state. This is called flip of proton. This is the schematic diagram. When a spinning nuclei absorbs electromagnetic radiation of proper frequency, it will excite to higher energy spin state. This is called flip of proton. So here no field, if the spinning nuclei is under magnetic field, external magnetic field, it will excite to higher energy state. The energy required for such a flip is given by h nu is equal to delta E, where h is the Planck's constant and nu is the frequency of radiation. The energy required for this transition depends upon the field strength h naught. This is because as the field strength increases, the energy gap between the two spin states also increases. Hence, the relationship between frequency of radiation and field strength is given by this equation, where nu is the frequency of radiation, h naught is the field strength, and gamma is the gyromagnetic ratio. In an organic compound, all the protons do not absorb at the same field strength. This is because the frequency at which the proton absorbs depends upon its magnetic environment. As an organic compound contains protons of different magnetic environments, different signals are observed depending upon the type of the protons based on their magnetic environment. This is the simple representation of NMR spectrum. Absorption of radiation is plotted against field strength. We'll get NMR signal like this. This is the construction of NMR spectrometer. The absorption of radio frequency energy by a proton depends upon its local environment such as electron density at it and the presence of other protons in its neighborhood. A set of protons with identical environment absorb radio frequency energy at the same field strength and termed as equivalent protons. All equivalent protons will give only one signal. Protons with different environment are referred to as non-equivalent protons. Each one of these will give one signal. So the number of signals equal to the number of non-equivalent protons. Examples are 2,2-dibromopropane. We have CH3, CH3. Here two bromine atoms are attached to carbon. So the environment for this proton and this proton is same. So 6 methyl groups on the two extremes are equivalent, indicated by letter A and A. Only one NMR signal will be obtained. Another example is N-propyl chloride. Here there are three types of protons, 1, 2 and 3, because Cl is electronegative. So this protons will be nearer to this. These will be a little bit far away from this, and this is far away from this. So this will have three different environments. We'll get three types of protons. These are called non-equivalent protons. So this molecule will give three signals. Another example is 2-chlorobutane. Here also we have 1, 2, 3, 4 types of protons. 4 signals are possible for this compound. Here there are some MCQs along with answers. This is the first MCQ. This is the second one. This is the third one. Fourth one. And thank you.